mean difference plot in SPSS, or alternatively called Bland-Altman plot, is a scatter plot. It is a graphical method used to examine whether two measurement methods agree and whether these two measurement methods can be used interchangeably. An example for that is using an old-fashioned mercury-based blood pressure device and using an up-to-date digital device for measuring blood pressure to find out whether the measurement from both devices agree, or the measurement or one device can be used interchangeably with another device, then the mean difference plot is the one to use for that. The plot is a scatter plot. The y-axis is plotted with the differences between the two measurements, and the x-axis is plotted with the average between the two measurements. And in the plot there are three major horizontal lines. One line is the bias line, which represent the mean difference, and another two lines for the upper and lower limits of agreement. Here in this SPSS data view, there are two variables, two measurements, measurement 1 and 2, and to find out whether these two measurements agree or can be used interchangeably, then mean difference plot can be used to visualize whether there is agreement between these two measurements. In a previous video clip, I had described one of the method to do it in SPSS. This is a second way to do and to draw the mean difference plot in SPSS. You need to have the latest version of IBM SPSS to do and to plot this graph. To draw the Bland-Altman plot, click on Analyze, scroll down to Descriptive Statistics, and then select the Bland-Altman analysis. A new window will appear to allow drawing of the graph. Drag the measurement 1 to this position and measurement 2 to this position. Click on Criteria. In the criteria, no changes here will be made, so just click on Continue. On the print icon, I'm going to select the mean differences and confidence interval, the agreement limits and confidence interval, and print details of the analysis. Click on Continue and then click on the plots. In the plots, I'm going to take the agreement limits, and then if I click on Continue and then OK, few tables and a plot are generated. From the second table here, it shows that the difference or the mean difference between measurement 1 and measurement 2 is equal to minus 0.049, which is very close to the value of 0. In the next table, the limits of agreement, the lower limit of agreement is minus 0.87, and the limits of agreement or the upper limit of agreement is 0.773. So this table shows the limits of agreement, the lower and the upper, and this table shows the mean difference, which is the bias, or that shows whether there is a systematic bias. Moving to the plot here, which is the Bland-Altman plot of differences between the two measurements, as shown here on the y-axis. The differences between the two measurement methods is plotted here, and on the x-axis is the mean between the two measurements. And in the graph itself there are three horizontal lines. The reddish line represent the mean difference or the systematic bias, and the two blue lines here, the upper one and the lower one, represent the limit of agreement, upper and lower. We'll do some editing for this graph to get rid of these lines here. So if I double click on the graph, a new window will appear here. Double click on these horizontal lines, select this section here, and then click on apply. Close this and close this again. Back again to the plot. As we look at the plot here, we can see it is a scatter plot with the dot randomly scattered in the diagram, and the systematic bias or the red line is very close to the value of 0, and there are few scores or data points that are outside the upper and lower limits of agreement. Fairly from this graph or plot, we can see that these two measurement methods do agree, and they can be used interchangeably, and there is no systematic bias. To confirm this mathematically, we could do one sample t-test on the difference. Before performing the one sample t-test, we need to generate two new variables in SPSS. Back again to the data view, we need to generate two variables. The first variable is the difference between measurement 1 and measurement 2. The second variable is the average between the measurement 1 and measurement 2. The way to do that is to click on transform, then select compute, then generate a new variable and give it a name of diff for differences, and then in the numeric expression select the first measurement, add a minus sign for subtraction, and then select the second measurement, and then click on OK, and back again to the data view here. A new variable is generated for the differences from each score in these two variables. The difference is calculated and recorded here. To generate the average, click on transform, compute variable, and give a new variable a name which is average, and then erase this numeric expression. In the function group, select statistics or statistical, and then select the mean. In this equation here, drag the first measurement into that position and the second measurement into the second, and click on OK, and back again to the data view. A new variable labeled as average is generated here, which is the average between the scores for each of the measurement 1 and measurement 2. So here we have two variables, the difference variable and the average variable. To move ahead and to do one sample t-test, click on Analyze, scroll down to Compare Means and Proportions, then select the one sample t-test. In this window here, drag the difference into the test variable. In the options, no changes, and we notice here that we are testing that the difference between the two measurement or the variable difference is equal to 0. i.e. the null hypothesis, there is no differences between the two measurements, they are similar, and the alternative hypothesis, there is a difference between the two measurements. If I click on OK, a few tables are generated as shown here. The mean and the standard deviation are calculated for the variable difference. The mean is minus 0.048. Moving to the second table, which is one sample t-test, what is of concern here is the p-value, the significant value. Since the p-value is greater than 0.05, then we will have to accept the null hypothesis, which indicate that there is no differences between the two measurements, i.e. there is no systematic bias, i.e. these two measurement methods do agree. So this confirming our observation from the Altman plot. To find out whether there is a proportional bias, then linear regression can be done. And the way to do that is to click on Analyze, select the regression, and then go for the linear regression in the new window here. For the dependent variable, select the differences, and for the independent, select the average. Then click on OK. And a few tables are generated here from the simple linear regression. What is of most important is the coefficient here. We need to have the coefficient, which is unstandardized coefficient, to be as close as to the zero value, and here it is minus 0.07, and we need this p-value to be greater than 0.05. So this table indicates that there is no proportional bias between these two methods. So this is the way to perform Bland-Altman plot in SPSS to test whether two measurement methods agree or not. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovie, Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovie, Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.